Right, so we're going to start off this lesson about the second derivative test by talking about how viruses spread. So a single person contracts the influenza virus, and now the flu epidemic is spreading through Calculopolis. The number of infected people 2 days after the initial outbreak can be modeled by that function, and the population of Calculopolis is 1,000. All right, so you can tell, like at the beginning, only one person has it, and then it's kind of spreading slowly, and then it starts spreading very, very quickly, and then it levels back off. And then it levels back off because so many people have already contracted it that there's not anybody else to give it to. All right, and then number 2 asks, when is the number of people infected growing the fastest? So to me, it's growing the fastest kind of in this section right here where the slope is the steepest. Now I put a little note also that f prime of t would have a maximum there where the number of people infected is growing the fastest. Okay, so to fill in this table, I would recommend you just use the graphing calculator. In y1, you would type in the original function. And then y2 is going to be f prime of t. So that's the derivative of that function that we typed into y1. So I just use the derivative keys in the calculator. And then if I want the function, we would put x equals x. And then for the second derivative on y3, it's going to be the derivative of the first derivative, which was typed in y2. All right, and then I already have that typed in. So what I'm going to do is I am going to turn off y1 because this table, we're not graphing, or we're not finding values of f of t. We're finding the first derivative and second. So I'm just going to turn that off, and then I'll go to the table, and then I can fill in the values for first and second derivative for particular values of t or x. So when t or x is 3, the first derivative is 3.64, and the second derivative is 2.1682. All right, so we would do that for those values. Just scrolling up and down the table. Okay, now I want to find that maximum of f prime of t, and I'm going to add it to the table. All right, so I'm going to add one more point. So I'm going to go back to the calculator, and I'm going to look at the graphs of these two functions. So I'm going to change my window. So I can tell by looking at my table that my second derivative is negative sometimes, and the lowest it gets is, we'll say, about negative 20-ish. Oh, wait, hold on. We're going from 0 to 21 on the x. And then on the y, we'll go from negative 20 to, the first derivative looks like it gets to about 150. Now let's just go by 5, see what this looks like. All right, so there's the graph of the first derivative. And there is the graph of the second derivative. Oh, I didn't go low enough. That's okay. All right. And so I want to find that maximum of the first derivative. So I'm just going to calculate it real quick. Okay. So it looks like when t or x is 11.454, the y is 150.75. Okay. And then I do also kind of want to see, and I'm just going to get it from the graph, what the second derivative is there. So right here is the maximum of the first derivative. If I go straight down, that second derivative value is 0. Okay, so now for which values is f prime of t increasing and which values is f prime of t decreasing? So we can get that from the table or we could get it from the graph. So from the table, you can see that the first derivative is getting bigger, bigger, bigger. Something happens in between 11 and 12. We know that that's the maximum. And then the f prime of t starts getting smaller. All right, and then you can see that on the graph. We're increasing on the first derivative until we get to the maximum, and then we start decreasing. So f prime of t is increasing from 0 until 11.454, and we'll tell y in just a second. And then f prime of t is decreasing from 11.454 to 21. Yeah, so it's just a 21-day period. All right, so then let's talk about y. So we talked about the first derivative test. Whenever the first derivative is positive, the function is increasing. And when the first derivative is negative, the function is decreasing. So that works when you are comparing second and first derivative. So when the second derivative is positive, the first derivative is increasing. When the second derivative is negative, the first derivative is decreasing. So our reason is because f double prime of t is positive, and then because f double prime of t is negative. All right, and then I'm going to hold off on 5. I kind of feel like you need to know the notes before you can answer 5. So we'll come back and answer 5 at the end. All right, and then we're also holding off on the back until we're done with the notes. All right, so on topics 5.6 to 5.7, we're going to be analyzing function behavior with the second derivative. And we'll go back and kind of review some of the first derivative stuff too as we go. All right, so concavity. The second derivative can be used to determine concavity. So if f is differentiable on the open interval, the graph is concave up. Concave up looks like a cup, is what I like to say. Concave up when f is increasing. F prime is increasing, sorry. All right. So if we're looking at f prime is the slopes of this function. So I have like a negative slope, we'll say like it's -1. All right, and then the slope here we say is like -1/2. and then the slope is 0. So those values are getting larger and larger and larger. Right, and then we'll say the slope is 1/2, and then the slope is 1. So f prime of x is increasing on that interval when the function is concave up. And then the graph on all of those little tangents I drew, the graph lies above the tangent lines. All right, and then we have the graph is concave down. So if we're thinking about the slopes here, so the slope, we'll say that's a slope of 1, and then that's the slope of 1/2, and then the slope is 0, and then a slope of negative 1/2. So f prime is decreasing there. And the graph lies below all of those tangent lines. All right, so we can use the second derivative to determine concavity. So if f is a function whose second derivative exists on the interval, the function, or if the second derivative is greater than 0 or positive, the function, that section of it, is concave upward. Okay. If that second derivative is negative, then that section of the function is concave downward. All right. And then we have a new thing that we're going to talk about today, which is the point of inflection. So the point of inflection is the point at which the concavity of the function changes. So where a function changes from concave up to concave down, or concave down to concave up. So in this case, for this graph, this right here is a point of inflection. All right, so the function must be continuous on the interval to contain a point of inflection, and the tangent line must exist at the point of inflection. Now, it can be a slanted tangent line, a horizontal tangent line, or a vertical tangent line, as long as it exists. All right, and then the point C, f of C, is a point of inflection on the graph. If either the f double prime of C is 0, or f double prime of C is undefined. All right. So let's talk about the second derivative test. So the second derivative test is used to find relative extrema, so relative maximum or relative minimum values. So we've already talked about the first derivative test, and we'll talk about it again, using the first derivative to determine extrema, but we can also use the second derivative. So it is important that when we're using the second derivative that this is the case, that f prime of C is 0. So we have a critical number. So we know that we have a critical number, and then we do the second derivative. So we find what the second derivative is at that value. If we get positive, that means that function is concave up. And I know that's a critical number. And so a critical number where a function is concave up produces a relative minimum. All right, and then we have this second derivative. And it's negative. It is a critical number. So a critical number where a function, the second derivative is negative, means it's concave down. Concave down with a critical number produces a relative maximum. All right. And then if we have a critical number, we do the second derivative and we get 0, the test fails. And you'll have to go back to the first derivative to determine, because we can't, nothing is conclusive in that case. Okay, so for this example, we're going to do lots of things. Some things we did previously, and then some things we need is new for today. All right, so our function is f of x equals negative 3x to the fifth plus 5x to the third. And we're going to do lots of things. So first thing we're going to do is find where the function is increasing or decreasing. And that, to find that, we use the first derivative. All right, so let's just start off and find the first derivative. And what we want to do from that first derivative is find the critical numbers. So we want to find where this derivative, first derivative, is 0. So we're getting 3 critical numbers here, 0, -1, and 1. All right, so what we'll do with them is go to a number line. I'm going to move it down slightly. And we're going to try to do as much as we can today without a calculator like we always kind of do. So it helps if we use kind of the factored version of the first derivative. And just think, like when we plug it in, we're multiplying positives and negatives together because we don't really need to know exactly what the value is. We just need to know if it's positive or negative. So everything that we put in to negative 15x squared is going to give you a negative. All right, and then negative, we would put in, we're going to have to put in -2, -0.5, 0.5, and 2. We're testing all of those in the first derivative. All right, then when I put -2 in, -2 plus 1 is a negative. And then when I put -2 in the last factor, -2 minus 1 is also a negative. So a negative times a negative times a negative is a negative. Okay, and then again, everything I put into that first factor is negative. Right? -0.5 plus 1 is a positive. -0.5 minus 1 is a negative. So a negative times a positive times a negative is a positive. Okay, so that's my sign chart. Right, and then remember that a negative first derivative means the function is decreasing. A positive first derivative means the function is increasing. So we would say f of x is increasing. And we could go all the way from -1 to 1, where we could break it up. I like to break it up because I feel like at 0, it's not doing either. It's just kind of pausing for a second, but you can still get it right the other way. All right, so that's the first part. The second part, we want to find the relative extrema. So we can use the first derivative like we did before. So when the first derivative changes from negative to positive like it did at 1, it creates a relative minimum. When x is -1, and we'll figure out what y is in just a second. And then when the first derivative changes from positive to negative, it creates a relative maximum, and that's what happens at 1. right? And then to figure out the y's that go with those, you just go back to the original function and plug in the values, and we get our relative maximum and our relative minimum. Okay, now I'm going to do an alternate way because sometimes questions are worded in a way you don't have the actual function, and you need to actually use the second derivative test to find the max and min. So I want to show it to you. So the second derivative test is an alternative way to find relative extrema. So we would go ahead and find the second derivative. All right, and the second derivative test uses the critical numbers that we got from f prime. So that's going to be -1, 0, and 1. All right, and what we would do is we would plug them in to the second derivative. All right, and when we plug in -1, we're going to get 30. We plug in 0, we're going to get 0. And when we plug in -1, we're going to get -30. All right, so what that means is -1 is a critical number. When I plug it into the second derivative, I get positive. That means the function is concave up at that critical number, which creates a relative minimum at -1, -2, which we found the other way. All right, then 0, we can't use the second derivative test. We would have to go back to the first. But then when we plug in 1, we get that the second derivative is negative, which means that at that critical number, the function is concave down. And concave down creates a relative max. Okay, so I do want you to know how to use the second derivative test, even though we found it using the first also. Okay, for D, we're going to find the points of for C, we're going to find the intervals where the function is concave up and concave down. That's where we use the second derivative. Okay, so we already found it. All right, so we are going to want to find when it is equal to 0, the second derivative. So that's going to give us two critical numbers, 0, and then that's going to be the square root of 1/2 and the negative square root of 1/2. All right. So that square root of 1/2 is going to be about 0.7. So when I'm testing numbers, I can test -1, -0.5, 0.5, and 1. All right. Now I've already put in -1 and 1, and I got 30 and -30. So that's going to be positive and negative, right? And then those two I can plug in and I get negative and positive, right? So whenever the second derivative is positive, the function is concave up. So f of x is concave up from negative infinity to negative 1 over the square root of 2. And, okay, go over, from 0 to 1 over the square root of 2. And then f of x is concave down whenever the second derivative is negative, which is going to be from negative 1 over the square root of 2 to 0, and 1 over the square root of 2 to infinity. All right, D asks us to find the point of inflection. So the point of inflection occurs when a function changes concavity, and this function changes concavity several times. So the function changes concavity at the negative 1 over the square root of 2, at 0, and at 1 over the square root of 2. All right, and then just because this is kind of crazy numbers, I just use the calculators to find the y. Right, and then finally, we are going to do a graph, and this is just a graph straight out of our head. So for E, all right. Let's start with relative maximum and relative minimum. So the function has a relative minimum at -1, -2, and a relative maximum at 1, 2. Okay. I also know I have 3 points of inflection. So at negative square root of 1/2, which is about negative 0.7, and then negative 1.2-ish, and then positive at 0, 0, and at positive 1.7, 1.2-ish. Okay. Then I know the function is starts off decreasing from up here. The function starts off decreasing and then also starts off concave up. So I'm decreasing and concave up from the beginning until here. We start increasing, but we're still concave up until we get to that inflection point. Let me try that again. Okay, but then we're still increasing, but we flop over to concave down. Then we're increasing, but we flop over to concave up. Right, the rest of the graph is concave down, but we are increasing and concave down, and then we're decreasing and concave down. So that's our cute little graph. All right, I am going to go back and do that very last part of the notes. So on example 1, we want to determine all the intervals where the first derivative is greater than 0 and the second derivative is less than 0. So if the first derivative is greater than 0, that means the function is increasing. The second derivative is less than 0. That means the function is concave down. So what we're looking for on the graph is increasing, but concave down. And the only section here is that. So we are going to say from B to C. Because f of x is increasing and concave down. Okay. And then for 2, for a twice differentiable function h of x, it is known that h prime of 3 is 0, so critical number. H double prime of 3 is negative 1.5, so which could be false. So a second derivative that's negative means the function is concave down there, so that's true. The first derivative at a value is 0 means that it's a point of inflection, a critical point there. Not sure about point of inflection, but because the 3 is a critical number and h double prime of 3 is negative, that means at that critical number we're concave down, and that does create a maximum. So C is the only one that's false, could be false. Okay, so on your assignment, these are the numbers I want you to do. The ones in parentheses, I want you to do like this big long example that we just did. And I'm not checking this until Monday. So don't wait forever to do it, but you have a little extra time, and it is going to be a 10-point grade.